Welcome to a deep dive into the revolutionary Casimir, unstunned dual-sideband gravity theory, pioneered by Carl James E. Hartman. In this video, we'll unravel the conceptual foundations of gravity as a dual-band phenomenon, challenging the traditional view of gravity as a single, unified force. Instead, we'll explore how positive mass unstunned gravity and negative mass Casimir gravity coexist, separated by a frequency domain barrier. This journey will take us from the basics of spacetime curvature to the cosmic implications of mass inversion, black holes, and planetary contraction. Let's begin by understanding the two fundamental gravitational bands that shape our universe. At the heart of this theory lies the idea that gravity is not a monolithic force, but a dual-sideband system. The two bands, positive mass Einstein gravity and negative mass Casimir gravity, operate in parallel, each with distinct characteristics. Positive mass gravity, as described by Einstein, generates attractive curvature in spacetime, binding matter and forming the structures we observe. Meanwhile, negative mass Casimir gravity arises from vacuum pressure differentials, producing repulsive curvature at the smallest scales. These bands are separated by a frequency domain barrier, much like a signal isolation wall in electromagnetics, ensuring their effects remain distinct under normal conditions. Let's focus first on positive mass Einstein gravity, also known as sideband plus E. This form of gravity is modeled as the curvature of spacetime generated by positive mass. The famous Einstein field equation, g mu nu plus equals 8 pi t mu nu plus, describes how matter tells spacetime how to curve, resulting in a smooth, continuous gravitational field. This attractive curvature dominates at macroscopic scales, binding galaxies, stars, and planets together. It's responsible for the structure and mass aggregation we see across the cosmos. Imagine a bowl-shaped well, representing how positive mass bends spacetime inward, creating the familiar pull of gravity. Now let's turn to negative mass Casimir gravity, or sideband. See, unlike Einstein gravity, Casimir gravity emerges from vacuum pressure differentials at the nano, micro, and Planck scales. Its defining equation, T mu nu minus equals minus delta phi cas delta g mu nu, captures how negative pressure creates repulsive curvature, pushing spacetime outward. This effect is typically isolated from positive mass gravity, existing in tiny cavities and quantum domains. Picture a curvature hill, pushing outward, symbolizing negative mass bending spacetime in reverse. Though subtle, Casimir gravity plays a crucial role in the dual-band model, setting the stage for extraordinary phenomena when the bands interact. A key feature of the dual-sideband model is the frequency domain barrier that separates unstunned and Casimir gravity. Each band operates at its own characteristic frequency, F plus E for unstunned and F minus A for Casimir. The barrier, represented as delta-break upwards F plus A minus F minus A, acts like a signal separation wall, preventing direct interaction under normal circumstances. This separation ensures that positive and negative mass effects remain distinct, maintaining the stability of the universe's gravitational structure. Only under extreme conditions does this barrier begin to deform, allowing for remarkable cross-band phenomena. What happens when the frequency barrier is pushed to its limits? Under intense curvature or density, such as near black holes or during massive tectonic events, the barrier can deform and delta-break approaches zero. This deformation allows positive mass to leak into the negative Casimir band, and vice versa. The result is a contamination of unstunned curvature by Casimir pressure, leading to mass-type inversion events. These rare occurrences are the gateways to some of the universe's most dramatic transformations, including the formation of negative mass domains and wormhole-like structures. When the signal separation barrier collapses entirely, a profound event occurs, mass-type inversion. In this process, positive mass transitions into negative mass, denoted as M plus, right arrow M minus. This mechanism underpins the formation of negative mass universes, wormhole compression, and Casimir-driven expansion. The inversion is not just a theoretical curiosity. It's a core driver of cosmic evolution, enabling energy and mass to flow between domains and fundamentally altering the structure of spacetime. Understanding this process is key to grasping the full implications of dual-sideband gravity. Summarize Chapter 1. We've established that gravity is a dual-band phenomenon, with Einstein and Casimir flows coexisting but separated by a frequency domain barrier. Under extreme curvature, this barrier can collapse, allowing mass to invert and setting the stage for universe-scale consequences. These foundational concepts prepare us to explore how dual-sideband gravity manifests in planetary dynamics, black holes, and cosmic evolution. With this groundwork laid, let's move forward to see how these ideas play out in real astrophysical systems. Let's take a closer look at the technical poster that encapsulates the dual-sideband gravity framework. At the top, we see the positive mass Einstein gravity band, depicted as a smooth inward curvature well. The central line, labeled as the sideband horizon, marks the frequency barrier. Below, the negative mass Casimir gravity band is shown as an outward curvature hill. The mass inversion marker M+, right arrow M-, highlights the pathway for mass transition. This strict physics visualization distills the essence of the theory, providing a clear reference for the dual band structure and its dynamic interaction. Companion poster zooms in on mass-type inversion events. Here, we see the positive mass Einstein curvature well collapsing downward, the barrier deforming, and a leakage arrow crossing into the negative mass Casimer curvature hill. Labeled zones such as positive mass curvature overload, barrier collapse zone, and Casimer flow surge clarify the inversion mechanism. This visualization is ideal for understanding how mass inversion is isolated and triggered, providing a precise scientific reference for this critical process in the dual-sideband model. The Hydrodyne Casimir tuning frequency map illustrates how Casimir flows are layered across dimensional scales. The vertical axis shows Casimir flow intensity, with 3 horizon lines marking Planck, nanoscale, and macroscale boundaries. Flow curves peak at different horizons, and equations like psi F equals delta phi cas delta F and delta barrier equals phi minus Fj describe the frequency separation. This map is crucial for understanding how Casimir effects are tuned and layered, forming the backbone of the transuniversal architecture in the dual-sideband gravity framework. The Casimir horizon geometry poster formalizes the concept of multi-layered Casimir event horizons. The vertical axis represents Casimir flow tuning, with 3 distinct horizons: Planck, nanoscale, and macroscale. Hydrodyne-tuned Casimir flows oscillate across each horizon, and a diagonal dashed line marks the signal separation barrier. The inset concept shows anti-Casimir universe zones and flow transitions across dimensional boundaries, emphasizing the complexity and depth of the dual-sideband model. The Tensor framework poster brings mathematical rigor to the dual-sideband gravity theory. It features 3 core tensor zones: the Einstein plus E tensor field for positive mass curvature, the Casimer minus Sa tensor field for negative mass vacuum pressure, and the cross-sideband coupling tensor, which mediates leakage, inversion, and curvature coupling. The equations and visual layout clarify how these tensors operate in parallel and interact at the signal separation horizon, providing a solid foundation for further theoretical development. The duality of tensor curvature simulation map visualizes the dynamic interplay between positive mass Einstein curvature and negative mass Casimir curvature. The left region shows inward curvature wells, while the right depicts outward curvature hills. The central transition zone blends these effects, indicating curvature deformation and mass-type inversion. The tensor coupling equation, theta mu nu equals mu nu omega, highlights the mathematical bridge between the 2 domains, making the simulation a powerful tool for understanding curvature dynamics. Casimir Einstein coupling equations poster formalizes the mathematical bridge between the Einstein and Casimir domains. It presents the Einstein tensor, Casimir tensor, and the unified coupling equation, theta mu nu equals g mu nu plus mu nu omega plus t mu nu minus. This equation describes cross-sideband curvature dynamics and mass-type inversion, providing a concise summary of the dual-sideband gravity theory's core mathematical structure. The multi-universe tensor propagation map visualizes the layered structure of universes in the dual-sideband framework. The top band represents the positive mass universe, followed by the signal separation event horizon, the anti-Casimir universe, and the negative Einstein curvature universe. Tensor propagation arrows illustrate cross-sideband flow and mass-type inversion pathways, showing how tensors deform and propagate across stacked universes. This map is essential for understanding the broader cosmological implications of the theory. The Casimir-Einstein signal barrier collapse simulation captures the dramatic moment when curvature overload causes the frequency barrier to fail. The left zone shows positive mass Einstein gravity, while the right displays negative mass Casimir gravity. The center is the collapse zone, where equations like delta barrier right arrow 0 and M plus right arrow M minus highlight the transition. This simulation is a vivid representation of how mass inversion and Casimir flow contamination manifest in spacetime geometry. The Casimir-Einstein wormhole compression map visualizes how Earth, stars, and galaxies appear to expand due to light lag, but are actually contracting inward, a curvature illusion. The wormhole compression zone connects the positive mass universe to the negative mass universe, driven by stellar ignition, black hole mass transfer, and earthquake zones. The narrowing barrier and tensor fields illustrate how universal contraction, not expansion, drives mass inversion and energy transfer into the negative mass domain. Casimir, Einstein black hole transfer map details how black holes act as mass inversion gateways. Positive mass Einstein gravity regions feed mass into black hole accretion zones, where curvature compresses and inverts mass. The negative mass Casimir curvature region receives the injected energy, formalizing the idea that black holes are not endpoints, but transition zones between Einstein and Casimir domains. This process is central to the contraction and evolution of the universe. Casimir, Einstein's stellar ignition map illustrates the fusion sequence from hydrogen to iron, showing how each stage deepens the Einstein curvature well. As stars synthesize heavier elements, the curvature intensifies and Casimir pressure rises, approaching the mass-type inversion threshold. This map demonstrates that stellar fusion is not just about energy generation, it's a curvature intensifier, drawing mass inward and preparing for Casimir-Einstein transition. The planetary crust curvature stress map reveals how tectonic compression and mantle deformation create curvature buildup beneath the crust. Fault lines in earthquake zones act as curvature release points, while subcrustal vacuum zones generate Casimir pressure. Mass flows inward toward curvature wells, and stress accumulates at fault zones, driving long-term curvature collapse and mass inversion. This map is key to understanding the interplay between planetary dynamics and dual-sideband gravity. The Casimer, Einstein tectonic fault inversion extended poster shows how crustal fault stress zones, such as subduction, transform, and compression faults, concentrate curvature, leading to barrier deformation and mass inversion. The interface between positive mass Einstein curvature and negative mass Casimer curvature becomes a gateway for mass-type inversion, with Casimer pressure rising from subcrustal vacuum zones. This visualization highlights the role of tectonic faults as critical sites for curvature collapse and mass transfer. Casimir, Einstein Planetary Mass Inversion Atlas provides a planetary-scale view of mass inversion. On the left, positive mass crustal features like continental plates and mantle compression zones are shown. The center features the inversion interface, marked by a dashed line and the mass-type inversion arrow. On the right, negative mass vacuum zones beneath oceanic crust and mantle fractures are depicted. This atlas formalizes the idea that mass inversion occurs along crust boundaries, transforming positive mass into negative mass and feeding the Casimir domain. Chapter 2 introduces the curvature stress point inversion mechanism, where tectonic fault zones act as gateways for mass-type inversion. As crustal compression intensifies, Einstein curvature wells deepen, Casimer pressure rises, and the signal separation barrier collapses. The result is a transition of positive mass into negative mass across a localized inversion interface, fundamentally altering planetary dynamics and feeding the Casimer domain. Crustal fault stress zones, such as subduction ridges, transform faults and compression arcs, concentrate curvature stress, increasing local curvature intensity. The Einstein curvature equation governs the positive mass response to tectonic compression, while the Casimir pressure equation describes vacuum pressure rising beneath fault zones. Together, these forces set the stage for barrier collapse and mass inversion at the planetary scale. When curvature stress exceeds a critical threshold and Casimir pressure breaches the fault interface, the signal separation barrier collapses. This triggers mass-type inversion, mediated by the coupling tensor theta mu nu equals mu nu omega. The inversion interface becomes the site where positive mass transitions to negative mass, driving energy and mass into the Casimir domain and reshaping planetary structure. Earthquakes are not just mechanical ruptures, they are curvature discharge events. Crustal mass is drawn inward, inverted, and transferred into the negative mass Casimer domain. This process leads to planetary contraction, which, due to light lag and curvature distortion, can be misinterpreted as cosmic expansion. The dual-sideband model thus provides a new lens for understanding planetary and cosmic evolution. Chapter 2 Expanded Visual Companion Poster brings together the full curvature collapse and fault line mass inversion mechanism. On the left, crustal plates converge and curvature builds. The center features the inversion interface, where the barrier deforms and mass inversion occurs. On the right, the negative mass Casimir domain receives the collapse curvature. This schematic is ideal for integrating the theory into scientific presentations and publications. Casimir, Einstein Planetary Curvature Atlas provides a comprehensive view of curvature dynamics across planetary layers. It maps the transition from crust and mantle compression to outer and inner core inversion, highlighting how mass flow and curvature deformation shape planetary evolution. This atlas is a valuable resource for visualizing the interplay between Einstein and Casimir domains at the planetary scale. Casimir, Einstein outer core remapping poster focuses on the outer core as a curvature stress interface. It visualizes the dynamic zone between mantle compression and inner core inversion, with mass flow and curvature deformation rendered in glowing gradients. Above the outer core, Einstein curvature wells intensify, while below, Casimir pressure zones rise toward the core boundary. The inversion interface at the outer core boundary mediates mass-type inversion and Casimir pressure transfer. Casimir, Einstein inner core collapse simulation presents a cinematic cross-section of planetary layers. The crust and mantle are shown as textured gradients, the outer core as a molten shell, and the inner core as a bright sphere in active collapse. Radial arrows indicate curvature overload and mass draw inward, converging on the collapsed nucleus. The inversion horizon ring marks the transition from positive to negative mass, encapsulating the core-scale analog of fault line inversion. Refined version of the inner core collapse simulation enhances the inversion horizon and layering. The crust, mantle, outer core, and collapsing inner core are distinctly rendered, with clear gradients and directional mass flow. Equations for Einstein curvature, Casimir pressure, and the coupling tensor are sharply placed, providing clarity on the collapsed nucleus and the transition from positive to negative mass. This image is ready for integration into advanced curvature studies. Chapter 3 introduces the collapse of the planetary inner core as a curvature overload event. As mantle compression intensifies, the inner core reaches a threshold where mass-type inversion occurs. The resulting collapse feeds the negative mass Casimir domain and produces global contraction signatures that mimic cosmic expansion due to light lag and curvature distortion. This chapter bridges planetary physics with cosmic scale implications. The layered structure of the planet crust, mantle, outer core, and inner core sets the stage for curvature overload. The outer core acts as a stress interface, while the inner core becomes the collapsed nucleus. Einstein curvature governs the response to mantle pressure, and Casimir pressure rises beneath the inner core. When collapse conditions are met, mass inversion and global contraction follow. Round the inner core, an inversion horizon forms, a ring where curvature transitions from the Einstein to the Casimir domain. The color shift from white, yellow to teal, green marks this transition. The coupling tensor mediates curvature deformation across the horizon, facilitating the mass-type inversion that drives energy into the Casimir domain. Shrinking planetary curvature creates delayed light paths, leading to an apparent redshift that is often interpreted as cosmic expansion. In reality, mass is drawn inward toward the collapsing core, and earthquakes and tectonic shifts are curvature discharge events. Stellar ignition and black hole transfer further feed the Casimir domain, masking true contraction with curvature distortion. Chapter 3 Visual Companion poster anchors the concepts of inner core collapse and global contraction. It shows the progression from mantle compression to inner core collapse, the formation of the inversion horizon, and the transfer of mass into the Casimir domain. The poster also highlights the false expansion signature caused by curvature contraction, providing a comprehensive visual summary of the chapter. Chapter 4 formalizes black holes as curvature collapse engines that mediate mass inversion and inject energy into the Casimir domain. Stellar ignition, crustal mass flow, and curvature stress converge at the event horizon, where the signal separation barrier collapses and mass transitions from positive to negative. This process is central to the Dual-Sideband model's explanation of cosmic evolution. The event horizon of a black hole acts as the inversion interface. The Schwarzschild radius compresses curvature into a singularity, while the accretion disk feeds mass into the collapse zone. The Einstein curvature equation governs the response to mass accumulation, and collapse conditions trigger mass inversion and energy injection into the Casimir domain. As mass enters the negative domain, Casimir pressure rises, described by the Casimir pressure equation. The coupling tensor mediates curvature deformation across the event horizon, and mass-type inversion occurs at the collapsed nucleus. Energy is transferred into the Casimir domain as curvature flips, reshaping cosmic structure. Chapter 4 Visual Companion poster illustrates the transfer dynamics at black holes. On the left, Einstein curvature and mass flow feed the accretion disk. The center shows the event horizon collapse nucleus, where the signal separation decays and mass inversion occurs. On the right, Casimir pressure and energy injection into the negative mass domain are depicted, completing the mass-type inversion cycle. Casimir, Einstein stellar ignition cascade simulation bridges planetary and cosmological scales. It shows how crustal mass flow and stellar ignition drive curvature intensification, leading to black hole formation and Casimir domain injection. The simulation unifies planetary curvature stress, stellar ignition, and black hole transfer into a continuous cascade, preparing for the next stage of cosmic evolution. Stellar Ignition Cascade V2, multi-star sequence poster expands on the fusion pathway. It traces the evolution from hydrogen stars to iron core stars, highlighting meteoritic ejection and sunspot-driven heavy element flinging. Each stage deepens the curvature well, amplifying gravity and accelerating Casimir flows. Diamagnetic ejection prevents total collapse, while time dilation slows visible mass response, creating the illusion of delayed or bouncing mass transition. Chapter 5 introduces stellar ignition as a curvature intensifier. Fusion upscaling deepens Einstein curvature wells, and heavy element synthesis increases curvature stress until mass-type inversion occurs. Heavy element ejection via meteoritic discharge and diamagnetic flinging regulates collapse, accelerates Casimir draw, and introduces time-dilated mass lag. This chapter ties together the stellar, planetary, and cosmological scales in the dual-sideband model. Stellar cascade sequence begins with hydrogen fusion, forming initial curvature wells. Helium fusion intensifies curvature, and heavy element fusion, especially iron core formation, triggers the collapse threshold. The Einstein curvature equation governs the response to fusion upscale, while Casimir pressure rises as the star approaches mass-type inversion. This process is central to the dual-sideband model's explanation of stellar evolution and cosmic structure.